So to start with our circular motion, we're going to begin with kinematics. And what does it mean when we talk about kinematics? What should that word tell you? Yeah, moving or motion. Okay, very good. So we're talking about the kinematics of circular motion, not the dynamics yet. Okay, when we say dynamics, we mean the forces and things that cause that change in motion. Okay, so when we're talking about kinematics, think about these questions that we're going to talk through here. What causes an object to move in a straight line? Straight line motion is that the net force has to be in the same direction as the motion I want to happen, right? If I want something to move forward, I need to exert a force in the forward direction, right? That's all we're talking about here. Straight line motion means it's in the same direction as the net force, okay? That's what we've looked at so far. Things that move from point A to point B, some force has to be exerted in that direction, and the net force overall has to be in that direction in order for the object to move in that direction. What do we have happen to an object to make it move in a projectile path? And what's a projectile path look like? Like what? Parabola. Yeah, a parabola, yeah. Yeah. Okay, an arc. So what happens to an object to make it move in a projectile path? Yeah. Yeah, we've got a force that's both horizontal and vertical. Okay, so our net force is exerted this time at an angle. We've got a force that's got both a horizontal and a vertical component. We're talking about things that are just simply moving or orbiting in a circle, not things that are spinning, not things that are rotating yet. We're just talking about things that are simply moving in a circular pattern. So we're looking at something or a net force being exerted at an angle. Okay. But this is not spinning things yet. This is not rotating things yet. This is just things that are moving in a simplistic circular path or an orbit. Okay, because we're going to get to planetary motion here at the end of this chapter. Okay, so when we're looking at goals for this chapter, we're going to talk about Newton's laws and how they associate with circular motion. We're going to look at velocity, centripetal acceleration of these objects, all that kind of stuff. So we're going to be able to connect Newton's second law with our different types of circular motion, velocity, acceleration, and the net force. Okay. What's the word uniform mean in this particular instance? Uniform circular motion. What do we know uniform means? The same. Good. Okay. So this is an object that moves at constant speed. This circular motion chapter is going to be something that's moving at a constant speed. Constant speed, but not constant velocity. How can that be? How can something move at constant speed but not constant velocity? Good. It has a change in direction. So as it's moving around the circle, we've got a constant change in direction. Right? It's constantly changing its direction. Okay, velocity has to have two things, magnitude and direction. So in uniform circular motion, the magnitude of velocity or the speed remains constant, but the direction is always changing. The direction is constantly or continuously changing. So the magnitude of the velocity or the speed, that remains constant. It's not speeding up or slowing down, but it's always changing direction as it moves in its circular path. Okay, so the magnitude of our velocity stays the same, the direction of our velocity changes. Do we have any acceleration in our object? What's acceleration mean? A change in velocity. Is our velocity changing? Yes, our velocity is changing. Okay, so velocity can be, a change can be either in the direction or the magnitude or both. Here, since we know acceleration is the rate of change of our velocity, we do have an acceleration. Okay, our velocity is continuously changing, although its magnitude or its speed stays constant. Okay, we still have an acceleration. velocity that goes into this uniform circular path, we look at infinitely small time intervals. Okay, we're not going to go into the derivatives of it. We're not going to go into all that kind of stuff. But we're looking at very, very, very small time intervals. And we want to see what the velocity of an object is at a very, very short time interval. Okay? So when we find a velocity of our uniform circular motion, we want to look at such a small time interval that we consider it 1 instant in time. Okay, we want to look at it at a certain point in time to see exactly what the velocity is at that instant. Okay, we know the magnitude of it is not changing, but the direction of it is. Okay, so with every instant that passes, the velocity is a little bit different. Okay, the speed or the magnitude of the velocity is not different, but the direction is. Okay, so with every passing instant, we've got a little bit slightly different velocity. Does that make sense? Okay. So this figure is in your book if you want to look at it a little bit closer in chapter 5. But essentially what we're looking at here is at point V1, at this point right here, if the object were removed from its path, so if for some reason if it was released of its circular path, it would fly off in a direction straight like that. Okay? And that direction right there is called tangent to the curve. Have you heard that term before? Something being drawn tangent to the curve. So what happens here is if I would release my object at this point in its circular path, it wouldn't continue in a circular motion. Okay, if I was like whirling something on a string and I released it, it's not going to keep going in a circle around me. It's going to fly off at a straight path from the instant at which I released it, and that's called movement tangent to the curve. Okay, so if at V1 I would release it at point A, it would travel in a path that looked like that, whereas at point B, it would travel in a path tangent to the curve in another direction. Okay, so although those points are similar on their circular path, they've got different paths depending on how far along in the orbit they are or in the motion they are. Okay, so our velocity of our object is always drawn tangent to the curve. Along with it you can, but you can do you can follow along with all the math that it takes on page 113 if you want, but what essentially we're looking for here is the centripetal acceleration, or the radial acceleration is what your book calls it. And the radial acceleration is found by taking v squared over r. So this subscript r stands for radial. That's what your book calls it. Some of them call him A sub c for centripetal acceleration. Means the same thing. Okay, centripetal means center seeking. I couldn't spell it right, so. Okay, but that's what your centripetal or radial acceleration equation is, v squared over r. So what this is telling us in words is saying is that an object moving in a circle with a radius r and whose constant speed v has an acceleration whose direction is toward the center of the circle. Okay, so your centripetal acceleration or your radial acceleration is what we call center seeking. Okay, it's being pulled toward the center of the circle as you rotate that object. Its acceleration is toward the center of the circle. And I'm going to draw it out here in a little bit so that you can see it. But our acceleration in this case is toward the center of the circle. let's take a look at our centripetal acceleration. Here's my object on a string. Okay. If I move it with some certain constant velocity and I have a radius, my radius is from the center of the circle to my object, right? So that little length of the string is my radius. As I increase my radius, does my acceleration increase or decrease? Okay, if I have a really, really small radius, and if I have a really, really big radius, which I'm going to probably hit myself in the face, okay, what happens? What happens mathematically if I make my denominator larger? The answer will be smaller. So that means as I increase my radius, okay, so as we increase our radius, our acceleration decreases, or our acceleration becomes slower. As we increase our radius, our direction doesn't change at as high of a rate. Okay, we move a smaller portion of the circle per second as we increase our radius. Okay, that means the acceleration decreases. As we decrease our radius, our acceleration should get bigger because we cover a bigger chunk of the circle per second, right? Our direction is changing at a greater rate. Does that make sense? All right. So when we draw our paths for our particular objects, our velocity vector is drawn tangent to the curve, and our acceleration vector always goes toward the center. So if I was going to draw my vectors here at a point here, let's say that my object was moving in the clockwise direction. My velocity vector would be drawn tangent to the curve, somewhere like that. And my acceleration vector would be drawn toward the center. Okay, there should always be a right angle between these two. Okay, those two should always be drawn perpendicular to each other. So if I asked you to look at the motion of an object at a certain instant, at this particular point right here, if my object was released, its velocity would fly off in that direction, yet at that instant it's accelerating toward the center of the circle. Do we know which is which? Frequency is the little f. Okay, and frequency tells us how many revolutions an object makes in 1 second, or in 1 minute, or in 1 hour. It's a revolution per time interval. So it's telling us how many times it makes it around its circular path in 1 minute, or second, or hour. We want ours to be in revolutions per second whenever we work with frequency. So 1 complete revolution means it travels around its circular path 1 complete time. Right? 1 revolution is its complete circular path 1 time. So we describe frequency as revolutions per second. Okay, or you'll see it revolutions per second. Okay? Whereas period, these two are connected with this equation here, but period is described with a big T. And that's because period is a time. Okay, period is the time required for it to complete 1 revolution. So period is a T because it's a time. Time required to complete 1 revolution. And these two objects are connected with this equation here. And that might be a good equation for you to write on your equation sheet. Okay, so this is under the chapter 5, circular motion. T equals 1 over F. You could also go ahead and write down your centripetal acceleration equation if you want, which was A sub r equals v squared over r. Okay, so that means period should be described with what unit? seconds. Okay, period is a time required, so period should always be in seconds. All right, we want our velocity to be meters per second. We want our acceleration to be meters per second squared. That means our time has to be in seconds. Okay, so now our time and our displacement and things like that are expressed in revolutions per second or in period. Okay. So if we're given one and we need the other, we can use this equation to connect the two. Okay. So when we're talking about circular motion, we want to know how far something has traveled in one revolution. We find the circumference of the circle, right? That's giving us distance. How far it's traveled in one revolution. The circumference of a circle is given with that equation, c equals 2 pi r. That gives us the distance traveled in one revolution. Okay, so this equation, the reason we use this is because it gives us distance traveled in one revolution. Right? During one revolution, it makes one complete round of its circular path, so we can find the circumference to find the total distance it's traveled. All right, and since we know that velocity equals distance over time, we can combine that equation for distance over the time it takes for it to travel one complete path. Right? Period is the time it takes for it to complete one revolution. This is the distance of it in one revolution. Okay, so velocity here equals distance over time, which in our circular motion terms is circumference over period. Okay, so this is another equation that you will use a lot. Okay, so that might be worthy of your equation sheet. This chapter has lots of little equations like this, lots of substitutions that can be made, lots of just kind of tweaks to your equations that can make things work. Okay, so there's lots of options for equations in this chapter. All right, so we're going to do some practice here. I'll give you some time to go ahead and get this problem written down, and then we'll work through it. All right, let's go ahead and pick things out of our problem here. So far, have we needed to use mass? Has that come into any of our equations yet? No, so we don't really care about that. Okay, that will come into play when we start applying forces and we start looking at the centripetal force that's used in these problems. But for right now, we don't need it. Okay, we know that our radius is equal to 0.600 meters. What do we know about this? 2 revolutions per second. What's that equal to? Yeah, frequency. So frequency is 2 revolutions per second. And we want to find centripetal acceleration. So I went ahead and put the centripetal acceleration equation up there. Do we have v squared that we can use? No. Do we have a way we can solve for v? Yes. Okay, so we need to use our velocity equation. 2 pi r over t. But how do we go from frequency to period? Because right now we have frequency and we need t. Yeah. So t equals 1 over f, which means t equals 1 over 2, which means it equals 0.5. Okay, so what that tells us is that since it can make 2 revolutions in 1 second, we know that it makes 1 revolution in a half a second. Does that make sense? We see the connection between those? Okay. So now we can go about solving for velocity. Velocity is equal to 2 pi 0.6 over 0.5. I usually just go ahead and use the pi button, and I leave everything in my calculator. That's our constant speed. So from there, we're going to plug in to centripetal acceleration, 7.54 squared divided by 0.6. So I'm just going to square it in my calculator, divide by 0.6. And our units for centripetal acceleration are meters per second squared. Very good. Okay, so these problems sometimes take a few steps, a few equations to get to our final answer. For example, here we had to take our frequency, convert it to period, and then find velocity, and then solve for acceleration. Okay? Any questions? So go ahead and write down what you need to, and then we'll start on it together. What should we do to our radius here? Needs to be in meters. So right now we're at 3.84 times 10 to the 5th, which means we need to be at 3.84 times 10 to the 8th meters. Right? We should have a greater number of meters than we have of kilometers. We have a period of 27.3 days. How do we convert that? Can we leave it in days? No. So we need to do a quick T-chart here to go from days to what? Seconds. Okay? So 1 day is 24 hours. 1 hour is 3,600 seconds. All right, so our overall goal here is to find our acceleration. And our acceleration equation is v squared over r. Do we have our velocity? No, we need to solve for velocity. Okay, so let's do that first. So I got a velocity equal to 1,023 meters per second. Yeah? Yeah, okay. From there, we're going to go plug that in our centripetal acceleration equation. Be careful when you are dividing by something in scientific notation that you either use the E button or you put that entire thing in parentheses. Okay, because if you don't, if you take 1023 squared divided by 3.84 times 10 to the 8th, it's going to take your whole answer times 10 to the 8th. So you would end up with something with an exponent, which is not what we want. Okay, use either the E button or put parentheses around that scientific notation. Okay, but is that what we got? 0.0027? Okay, so our moon is not moving very quickly. Okay, it's not moving very quickly toward the Earth is what we're saying. Its centripetal acceleration is not much. Even though it's moving at a rate of 1,023 meters every second in its orbit, its acceleration toward the center of the Earth is not great, okay, because the radius is so large. Okay? All right, any questions there? Okay. The ball moves at constant speed of 4 meters per second around a circle with radius of 0.25 meters. What's the period of the motion? So here are the values that are given to us. They gave us velocity and they gave us radius. So we can use our velocity equation. To solve for t. What do we do? What's our shortcut if we have an equation like this where we're solving for variables on the bottom? Switch these two places. Okay, so it would look like this. T equals 2 pi times 0.25 over 4. And that means I got t to equal about 0.4 seconds. Yeah? Okay. All right, questions? All right, this last problem I want you to do with your partner, you're going to have to just work to figure out a way to figure this one out because it's a little bit more conceptual. It's a little bit less straightforward, but I want you to see what you think about it. Okay? A race car traveling at constant speed around a circular track, what happens to the centripetal acceleration if the speed of the car is doubled? Okay, does the acceleration double? Does the acceleration get cut in half? What happens to its acceleration? Okay, so you might have to try some numbers. You might have to try to think about what the equations look like. I want to give you about 4 minutes, and I want to talk about it as a class. This times 4. So as we increase our speed, does our radius change at all? No, the radius doesn't change. So I picked two sets of numbers where we had a velocity at 200 meters per second. I got an acceleration of 800. If I doubled my speed to equal 400 meters per second, my acceleration was 3,200. So if I compare those two numbers, 3,200 is 4 times as large as 800. Okay? And the reason that changes drastically is because of the square. Okay? If these two were directly related, if there was no square, one would double, the other would double. Okay? But these are exponentially related, so we've got to take that square into consideration. Okay? So when we talk about something doubling or getting cut in half, we have to take the exponent into consideration, so it's best if you just try it with numbers. Okay? All right. That is where we're going to stop for today.